So let's take a look here at the material that is covered in this. Notice we start all the way at section 11.4 because we've already done 11.1, 11.2, and 11.3 in previous chapters. Okay, so we are going to focus this chapter on solids. Okay, and so for the most part, that's going to be surface area and volume of three-dimensional shapes. And so introducing the three dimensions, we're going to talk about a few types of solids, the first one being polyhedron. And this is just a solid that's formed using only polygons. So all shapes, or all of the sides on a polyhedron are going to be triangles, quadrilaterals, any other type of polygon. Okay, they don't necessarily have to be in a specific pattern as long as they're connected only with no curved shapes. Okay, and there are 5 polyhedron that are called the Platonic solids. You see all 5 of them listed right down here. These are the 5 Platonic solids. And what that means is not only are all of the sides polygons, they're all regular polygons. Polyhedra is the plural for polyhedron. So polyhedra formed by the same regular polygon. It's called Platonic solids. They're also called regular polyhedra. The 2 most common ones, or the most common one, is this: the square or the cube. Okay, it's all squares, okay, or regular quadrilaterals, and then also this pyramid here with all equilateral triangular faces. Those would be the 2 most common ones, but there are 3 others, and you can see them there. It's just going to be a matter of can you recognize them on some homework problems. Right, when you're talking about polyhedra, you can see up here that there's a couple terminology. A vertex is the point where edges intersect. The edges are the sides or the segments that connect vertices. Okay, and then the face is just the plane that's formed. Okay, or a portion of the plane that's formed or that's the boundary of that side. So when you are looking at polyhedron, a couple things that you are going to be asked to do is first be able to count these. Okay? So if you look at this figure right here, see if you can count the vertices, faces, and edges on it. Okay? So right here, count the vertices, the edges, and the faces. See if you can fill in those. And then do this calculation here. What's the total sum of the faces and vertices added together minus the edges? So if we count vertices as you're doing that, 1, 2, 3, 4, 5, 6 vertices. How many faces? If you look at these faces here, what you can see, or I'm going to count the edges first, I guess. So here's 1, 2, 3 edges here, 4, 5, 6 edges on the sort of parallel triangle, and then 7, 8, 9 edges total when you count the pieces that connect those 2 triangles. And then when you look at how many faces there are, so if we look at this triangle, here's 1 face, the triangle behind it, 2 faces, and then there's a rectangle, rectangle, and rectangle. So there's 3 faces connecting those. So that's a total of 5 faces in this polyhedron. And so if you take the faces plus vertices minus edges, you have 5 plus the vertices 6 minus the edges. And what you should get with this is always 2. Okay, and that's going to be true of this situation. F plus V minus E is always equal to 2 for any polyhedra. Okay. We're not going to spend much time on those other than you do need to be able to answer some homework questions involving them. The majority of what we're going to spend our time looking at are some specific types of three-dimensional figures. Okay, and the specific types are these. We'll go through them. Okay, prisms. Okay, so I'm going to kind of go through and I'm going to define these here and then show some illustrations of them. So a prism is a solid that's made up of two parallel and congruent polygon bases. That are connected by parallelograms. As the lateral faces. Okay, and so if you took an example of a prism, so if we have a triangular base, okay, bases for prisms come in parallel and congruent pairs. So that means we would have another parallel and congruent triangular base. And these are connected by parallelograms. So if I can connect these with vertical lines, for the most part, we're going to be focused on what are called right solids. And in right solids, those parallelograms are all right angles, which makes it rectangles. And when you name a prism, you're going to name it based on the shape of its base. So here you have these parallel and congruent bases that are triangles. So this is said to be a triangular prism. Okay, when you find these, we'll talk a little bit more about the dimensions of these, but for right now, we're just identifying what they look like. So again, if you took, let's say, a trapezoid, and you had another trapezoid that was parallel and congruent to it, and then you connect each of these vertices, the corresponding vertices, with a straight line, what you wind up with here is a prism. And keep in mind that when you look at this prism, the bases aren't the top and bottom, right? Because if I looked at the top and the bottom, are those parallel to each other? Yes, but are they congruent to each other? No, and they're not connected by rectangles, they're connected by different types of figures. But if I look at this trapezoid and its parallel and congruent base here, and then those are connected by these straight lines that form rectangles, I see that this is a trapezoidal prism. The bases can be front and back, they can be the left side and right side, they just have to be parallel and congruent to each other. Right? The other polyhedra that we're going to focus on are pyramids. And these are solids that are made up of one single polygon base. And that base is going to be connected by all points along its perimeter to a common vertex. So if we do kind of the same thing, so if we start with, let's say, a triangular base right here, so I'll shade it as the base, and we connect each of those points to one common vertex, here, here, and here. Okay, that is your pyramid. It's named by its base as well, so this is a triangular pyramid. And you could also have a trapezoid that if you connect everything to one single point, and the easiest way to model that is just to connect each of the vertices to that point. Again, there's your vertex, and this would be a case of a trapezoidal pyramid. All right, so based on what you see here in these couple examples, see if you can answer the question right below and find how would you name each of those shapes. or each of those solids based on being a prism or pyramid, what's the shape of their base? Right? And so which of those names would you give each one? So even though most of the time bases are going to be the top and the bottom piece, it's not always the case. Okay, so for prisms, the bases are the parallel and congruent polygons. And for a pyramid, it's the polygon that's connected through all points to one common vertex. Okay, so here in this first example, we see the top and bottom aren't congruent to each other, so our bases are these front and back sides. It's the shape of a trapezoid. Since there's parallel and congruent bases here, it's a prism. Next, everything comes to a common vertex, so we know that this is a pyramid. Count the number of sides of its base, so 1, 2, 3, 4, 5. 5 is a pentagon. So you might need to refresh and see the names of the different types of polygons. Next, we have 2 parallel and congruent bases, so we know this is a prism with a shape of 1, 2, 3, 4, 5, which is pentagon again, so pentagonal prism. Next, we have a prism again, parallel and congruent bases, but 1, 2, 3, 4, 5, 6 sides, so hexagon. Here we have a vertex, so a pyramid from 1, 2, 3, 4, 5, 6, hexagon again. And then lastly, we have a common vertex, 1, 2, 3, a triangle. So it's a pyramid with a triangular base, so a triangular pyramid. So that's the naming conventions for those solids. Right, so these are the 2 main types of polyhedra that we're going to look at. So again, these are formed using only polygons. Okay, the other main types of solids that we're going to look at are solids of rotation, so they do have curved surfaces. Okay, and so a solid of rotation or solid of revolution is a solid formed by rotating a 2-dimensional shape around an axis of revolution. Okay, so these are also called solids of rotation. Okay, so solids of rotation or solids of revolution. Okay, and there's 2 ways to define each of these. So the first way, I'm going to go through and define it in the similar way that we defined prism and pyramid. Okay, and that is here we're going to take a solid that's made up of 2 parallel and congruent bases, but this time they're going to be circular bases. So this is a cylinder that are going to be connected by what amounts to a rectangle curved about the lateral surface. And so this one, if you look at by the definition, you have 2 circular bases that are parallel and congruent, and they're connected by this curved rectangle. Now think about what this looks like. It's called a net. If you unrolled this, you would have one long rectangle with a circle on either end. And that would give you your solid if you rolled it up. So you could actually cut this solid out on a 2-dimensional shape, and then if you rolled this back up, you would get your cylinder. Again, these are your bases. They're both circles. Okay. Now I'm going to go through and I'm going to, for the cone as well, I'm going to define the cone in a similar fashion to pyramid. And then I'll come back and show you the other way to define all of these. Okay, so a cone is going to be a solid that's made up of 1 circular base And just like a pyramid, it's connected to one specific point called the vertex. Okay, and so if you took your circular base here, and from every point along that base, we connect it to one common vertex, you have your cone. Okay, the net of a cone is going to be basically a sector with a circle at the end. Okay, and then finally, the last definition here, or the last solid of rotation we're going to look at, is a sphere. And first, just by the definition, it's the set of all points a given distance from a fixed point. Now remember, this was how we started the definition of circle, right? And we said that it was wrong because a circle needs to be limited to 2 dimensions. So the only difference between this definition of a sphere and the definition of a circle would be adding the word coplanar in front of the points. So the set of all coplanar points a given distance from a fixed point is a circle. The set of all points would include, if we had one point here, all points along this circle of it, but then also all points that are that same distance, the radius from that center in all dimensions, that would be a sphere. All right, so these would be the examples of the 3 main solids of rotation. These aren't the only things. You can take any type of 2-dimensional shape and rotate it to get a solid of rotation. Okay, but these are the ones the main ones that we'll focus on. Okay, and there's a second way to define each of these through their rotation. So I'm going to talk through that really quickly. A cylinder can be thought of as a solid that's formed by rotating a rectangle about one of its sides. So if we took a rectangle right here and we rotated that rectangle at one of its sides, so it rotated and came back and formed that solid, you would see that it forms this cylinder. Okay? And so the sides of the rectangle would be a radius for this bottom piece and the height of your solid for the top piece. So again, that would coincide here to the radius and the height of this cylinder. A cone is going to be a solid that's formed by rotating a right triangle. About one of its legs. So here, if you had this right triangle and you rotated it along one of these legs, notice you form that cone. Once again, the leg of the triangle will be its radius and its height will be the other leg. The hypotenuse of that right triangle is said to be a slant height, which is called L, or abbreviated L. And that's just the distance from the vertex to the edge of the base. And then finally, a sphere is going to be a solid that's formed by rotating a semicircle. And that happens across its diameter. So if you took a semicircle and you rotated it about the diameter, you form that sphere. And it also has either this radius is the radius of the semicircle. The diameter of the semicircle is also the diameter of that sphere. Okay, so those are the 3 solids of rotation that we'll focus on when we start talking about surface area and volume. See if you can answer this. Based on those definitions, you should be able to just find them directly and associate them with the correct answer. A sphere is a semicircle rotated about its diameter. A cylinder is a rectangle rotated about one side. And a cone is a right triangle rotated about a leg. And so that's just based solely on the definition from the rotation. All right, obviously this is just an introductory chapter. We're not going to go into the details of labeling too much of this. The only other thing that you're going to see on this short assignment for this is the idea of a net. A net is just a two-dimensional pattern to represent three-dimensional solids. And so what you can see right here is if your lateral faces are triangles like they are in pyramids, you should have triangles on each of the edge of a polygon. If you are looking at a prism, then you should see two parallel and congruent polygons opposite each other on a polygon or a rectangular face. And then you should see a series of other rectangles as those faces. So if you look at these nets below, see if you can match the net that's shown below to what that would look like as a solid. Okay? What would the base shape be, and would it be a pyramid or prism? Okay? And you can also, again, see nets for the cylinders and cones that we saw on the previous slide. So often when these are represented in their three dimensions, the perspective will be skewed a little bit. So even though that looks like it's more of an equilateral triangle, it'll be kind of perspective, like it's tilted to the side, and you get this as the representation. So this is going to be a pyramid. It has 1, 2, 3 sides on its base. So the base is a triangle, so a triangular pyramid. Here we have our two parallel and congruent bases. They are, so again, kind of the perspective of it is skewed a little bit. Notice I have parallel and congruent bases that are connected with what are more like squares here, but this is the representation. And so when you're looking at it, your base is 1, 2, 3, 4, 5, 6 sides. Hexagonal, and it's all rectangular faces, prism. Here we have 1, 2, 3, 4, 5, so we have a pentagon. And it's two parallel and congruent bases, so once again, if you think of this as being your parallel and congruent shapes connected by straight lines, so that gives you a pentagonal prism. And then lastly here, you have your two bases. Your bases are either rectangles or, again, if you called this a square prism, that would work. But is there a choice for square prism in this set? No. If there was, you could call that a square prism. But right now, we just know that these are rectangles. And again, here's the side. So if you had your two rectangles. Now, these often tend to be kind of skewed to the side as well. So there would be the three-dimensional representation of it, but it is a prism also.